Hi scholars, it's great to have you back today, ready to go, focused, and we're going to learn a lot. I'm Brooke Woods, I'm at Harriet Ross Tubman School 31, and today we're going to learn a little bit of science. I'm going to infuse a little bit of math too, so I don't want anybody to get too scared, because we can all work on this together. Our first essential question for today's lesson is, that I want you guys to actually think about here for a minute. Will an object sink or float? I'm going to give you a minute to think that essential question through. And in that, retrace in your brain all of the times that you've actually seen that occur, whether it's in a pool, maybe a bathtub, a kitchen sink, or in your science classroom. Hopefully you've had some time practicing this. And in your mind, instead of just considering taking an educated guess, right? If I were to show you this block or this rock, for example, and say to you, how will you know if that sinks or floats? Your educated guess, which is that's right, hypothesis, could be correct. But in order to ensure that before you do the actual experiment, that you're on the right track, would be to solve for a science property. So if you can dig back in your minds, and I know it's been a minute since we've been in school, that you learned about a science property called density. So today's lesson split into our different 3 segments. So we're going to break down how to find density. We're going to focus on the calculations, which is where the math comes in, and the actual doing. So that next time that you're at the point where you're considering this essential question, would it sink or float? You'll have another additional procedure or step to be able to do to actually figure out the answer. Okay? So this property that we're going to learn about is actually called density. And it's a tough one for students to learn or remember in middle school. And I'm going to start by writing it up here. At home, where you're writing right now, hopefully you're taking active notes while I'm sharing my notes with you. On a piece of paper is fine. I'd like you to start by writing down the word density. And hopefully in your mind you're having some firings like, what was density connected to? When did my science teacher teach it to me? Maybe it was in and hopefully you're thinking the intro to science unit, the measurement unit, things of that nature, usually in the beginning of the year. You could have learned about density in 6th grade, 7th grade, or 8th grade. So the overall science property we're going to talk about today is density, but in order to figure that out, we have to break it down. And the first thing we're going to focus on is mass. Okay, so this word mass, it is my sincere hope that you all know and can recall what that is the matter inside an object. And for the sake of today's experiment, the amount of matter inside of an object, we're going to focus on these materials that I brought with me today. So for example, this block of wood. For those of you who can't remember, and hopefully you're looking here at the science equipment that I have with me to do this demonstration, this piece of equipment right here is called the triple beam balance. And it's really unique because it finds mass of any shape. Actually, it could be the block, it could be an irregular shape like this marble or this rock here. But it's unique because it solves for this property in grams. And we're actually going to be using the unit for grams with a G. So our unit for grams is going to be a lowercase g, a lowercase g. And when you look at this piece of equipment called the triple beam balance, hopefully it starts, or hopefully you've had some exposure to it, and it starts to really get your mind flowing. Where could I initially look to find the mass of this object? Now, one thing that I want you to remember before you ever balance anything out on one of these, that you make sure that the white line here is balanced with the 0. And that your riders are all set to the 0 side of each of their scales, right? We have these 3 different beams here, which is why we call it a triple beam balance. And this pan, as long as it's balanced, is where you're going to set your objects. So you set your first object on there, and you'll see that the line moves up. Now this middle one is where you always want to start, the 100-gram mass. And there are little notches that you would move over and make sure it actually falls in the notches. One thing that students tend to have an error on when they use this, if anything, is ensuring that it's actually in a notch. Now, if the line goes all the way down, that means that this material or this object that you have on here is much less than a 100-gram mass. So we're actually going to go back to 0. And after your 100 gram, you're going to go to 10. And what you do here is you start out in increments of 10. You go all the way over in each of the notches until, oh, and you could see that it was starting, the arm was starting to move down until it goes all the way down to the bottom. And when you're here, it's actually an indicator that you had to go back 1. Because now you know that the mass for this block is actually going to be between, and hopefully you guys can see the scale here, the 40 and the 50. So what we do now, because we have to have it more specific than that, is we use the front writer. And this goes by single grams in the front. The best part about this is that when we're doing science, you have to round everything to the nearest tenth, which is 1 decimal to the right, 1 place to the right of the decimal. And this actually rounds it for you, just like that. So when you take or you read anything off of the scale, and this actually looks pretty balanced from here, it reads as the tenths place. So what you're going to do right now, where it's balanced, you're going to actually add up your riders. So this back mass is 40 grams. Your front mass is 6, 0.1, 0.2, 0.3, and 0.4. Hopefully you guys can see these tiny little black dashes right in here. It's not quite halfway, which would be 6.5. So 46.4 is actually going to be our total mass for this object. Okay, let's just go back over the front again. Each of these little dashes is a 0.1. So 0.1, 2, 3, 4 is where the 6.4 lands. And then you get a total mass for this block of 46.4. So what we're going to do at this point is go to the board and your paper, and we're going to take that down as our first piece of data. So we want to do M equals, for mass, 46.4 G's. And don't forget, your G should be a lowercase g every time that you're not writing out the full word grams to indicate the unit, okay? So our first step here is solving for mass, or calculating mass, I should say, finding it. It's the amount of matter that's in your block, or in your rock, or in whatever it is that you're deciding, is it going to sink or is it going to float? Okay, so we've now done step 1. We found the mass. We found it accurately. Don't forget, when you're at this point, you would take your material off and you would move your riders all back to 0 before you ever wanted to start the next object. So for this, we've found mass. This is our first step to actually solving our essential question. Okay, and next we're going to focus on volume, and we'll do that right after our break. See you then. Welcome back, science scholars. For our next segment, we're going to be focused on the second part of our process, or procedure, as we like to call it in science oftentimes, of solving our essential question. How will we know if an object will sink or float? Beyond taking your educated guess, right, or making a hypothesis, and beyond just saying, let's set this block in water and see what it does. So we're going to then move from the idea of mass, which is the amount of matter inside of an object, to this new word that I'm about to put on the board here called volume, which is the amount of space that an object takes up. And we had taken the information from the mass of this block, which I have labeled 8A here, And I have the math up there still, which was in grams. So I want to keep you, your mind focused on this too, right? So we have our first piece of data. And now with this idea of volume, we're going to take our second piece of data. So on your notes, please, and I'll give you a minute to write underneath where you've already written down your information for mass, add our next important word, volume. And we're going to use the same object, and we're going to solve or find the volume for this object. And this is the amount of space an object takes up. So I hope that you're putting in your brain or recalling from your brain from when you learned in science class the difference between mass, okay, the amount of matter that's packed into the object, versus the volume, the amount of space that the object actually occupies or takes up. Now, unique to mass, where we only were using grams, there's actually going to be two units that we use when we calculate or find volume. And the first unit that you could possibly use is going to be centimeters cubed. I'll put a parentheses around it. And our second option, and we use this one primarily when we're finding the volume of an irregular shaped solid or a liquid. And we'll talk about a graduated cylinder in just a second. The unit for that is actually milliliters. And you have to be real careful on your active notes right now with me. When you write down this unit, it's a lowercase m and an uppercase L. So we want milliliters like that. So this is unique, right? We have two different options, and it actually depends on what we're solving for. So I'm going to show you through this demonstration a little bit about which one would be the right choice based on what your object you're actually looking at. So if we're focused on our 8A block that we had for math from segment 1, okay, you're actually going to use a piece of equipment that I know you all recognize and know how to use. This is the beauty of volume. It's a ruler. And in science and math for middle school in New York State, we only use the metric system. So you can see on my ruler that the actual unit here is centimeters. Yeah, is that better? Centimeters. And each one of these little lines is actually 1/10 of a centimeter, which is again ideal because we have to round, as we did there for mass, all of our answers for volume to the nearest tenth. So when we find our volume of this regularly shaped solid, we use something as simple as this ruler. And we're actually going to break that down in a second. Before we get to that part though, I want to show you, in case you were thinking, well, Miss Woods, what if I don't have a regular shaped block? You would actually have to use a tool or a piece of equipment more like this, which I have here for you guys, which is a graduated cylinder. And this is where your milliliter unit would come in. If you're focused on an actual liquid, and that's the thing that you're trying to find the volume for, you would look at the top height of the water level, which we also refer to in science as the meniscus, and you would use that height to read the scale and determine how many mils of that liquid you have. If you needed to do an irregularly shaped solid, like a marble or a rock, you would use the water displacement method. So again, you would use this graduated cylinder. You would carefully tip it sideways. You don't want to splash any water out, or that would be like, you know, student or user or scientist error, right? So you let it roll down gentle. You would then record your new water height on a flat surface. Remember, it's important. Move your body, not your science equipment. Because if you move it, you won't get the correct meniscus. So now you would look for your new water level height, and you would be able to subtract your original water level height, and there you would get your volume of an irregular shaped solid. You can do this over and over for as many different shapes or objects that you have. As you can see, I have different shaped marbles and things. This rock, obviously, I would need a beaker for because it wouldn't fit inside my graduated cylinder. But you can do the same water displacement method for irregular shaped solids as what I just showed you here. So we're going to go back to focusing on our block, because this is the more straightforward way and the way that we oftentimes practice in science class. And it's the one that we took the data on with our original segment here for mass. So we're going to have to actually find 3 different dimensions here. And for volume, and hopefully through math class, and I know you all love math so much, that you remember that volume actually has 3 parts to it. You have your length, your width, and then don't forget to turn it sideways and find that height as well. Okay, so we have our length, our width, and our height. So what we do when we set up our formula to solve for volume, we write V equals. So there is an additional step before you actually get to writing your answer down. And you would, to get your length, you're going to set your 0 up at the far left-hand side. And you're going to go all the way down here to where the end of your block is. This is at 8.678. So this is actually at 8.8 centimeters, our length. And we're going to actually take that data down. So we would have, oh, Miss Woods, sorry students, Miss Woods did it wrong. I'm not even paying close attention. Some of you probably caught me before I even noticed. It's actually, I have to be more careful with my scale, 8.1, 2, 3, 4. It's actually 8.4 centimeters. So we're going to start with our length. We have 8.4 centimeters. And we're going to multiply that by our width. So now we're going to turn it sideways. And we're going to, more carefully than I did the first time, look to record our width. And we're looking at 5.6789. I'm not sure if you guys can see that, but we're looking at 5.9 centimeters. And lastly, we're going to multiply this by our height. So you have to find that 3rd dimension. You turn it on its side. And here we're looking at a height of 1.6 right on our ruler. And the best part is when we enter these points of data into our calculator, when you're multiplying 3 digits like this, you do not have to do it in any particular order. So you can enter them into your calculator as they appear here, and if you had taken like the height first, that would be totally fine. So you want to do your 8.4 times your 5.9 times your 1.6, and you can see here we have a total of 79.296, and we need to round that. So we look to the digit after the decimal, we use the actual hundredths place number, and we say 5 and above, give it a shove, which is going to take us up to the 5.3. So when we write our final answer down here, we're looking at 79.3 centimeters cubed. So keep that data in your mind. We're going to take both of these for our 3rd segment. Come back with me in a few minutes, and we're going to figure out how to figure out will it sink or float. Science scholars, thank you for joining me to figure out the last step in our procedure for our essential question. We talked about that when you see an object, like a block or a rock, oftentimes you either want to jump right into the experiment portion, right? See if it floats, or make that hypothesis before you take real data or do a calculation like we're about to do. But here we're actually going to, in today's lesson, figure out a way to give yourself that extra edge, right? That extra little bit of information so you really do know before you go ahead and do the experiment portion. So our last science property, and this is the most difficult one, is solving for density. We're going to take our mass that we have found and our volume that we have found and turn those 2 things into density to then see how it compares to water. So before we get to our actual calculations, I want to show you this idea of this bowl of water. So I know my drawings aren't great, but that is a bowl, okay, just like this one. And at some point in the middle of it, it really doesn't matter where, okay? If you could start to draw your bowl on your guided notes, please, or your active notes. We're going to draw a water line, maybe 2/3 of the way up, if you can draw with me. Okay, so draw your water line up here. And one thing that we have to remember, and the reason that we scientists oftentimes use water when we're talking about density is because it's a very simple, well, we can find a lot of it, right, for our experiments, but it's also a very simple value. It's just 1.0. Okay, so the density of, this is kind of bothering me that I chose red, so I'm going to go over it in blue, but the density of water is 1.0. So go ahead and write that down. It's not just 1, it's 1.0 because we have to round to the nearest tenth. And there are 2 units in our water density as well. So you have 2 options, and that was based on the volume that you would have found. So oftentimes, because water is a liquid, you're going to see written as grams per. So as you're writing in your active notes, go ahead and do that fraction symbol, and then it's grams per milliliter, little m, big L. So your paper should look exactly like mine in your drawing. So now we know water's density is 1.0 grams per milliliter, and we use it because it's a nice even number, right, to do our math with and to do our comparisons, and we have a lot of water available. So when we're finding our actual calculation here for density, okay, we are going to use the formula that I know you can remember if you think back hard enough. And we're going to use D for density. D equals M for mass over V. So for this formula, I'd like you to copy it down exactly as I have it. And our first step for figuring out this answer here for density is going to be to substitute. And this is like a basic math problem that I know you've done a lot of times. Perhaps not correlated to density, but you've done something similar. So what we're going to do for our block 8A, as I had it labeled, we're going to take our mass, so 46.4 grams, and substitute it in our top part of our fraction for mass. Okay, and we're going to get our fraction line there. And I hope you're already thinking, hey, Miss Woods, I know what to do next. I'm going to take my volume, and I'm going to substitute it in down here, right where volume goes. So we'll take our 79.3 centimeters cubed. And we're going to put an equal sign. You might not be running out of space, but I kind of am, so I'm going to move my answer down here. And I'm going to rewrite my D so I remember in my brain, hey, I'm looking to solve for density here. Now, really important as you're using your cell phones or you're using your calculators, or if you're just watching me do this calculation, whenever you're doing a calculation with a fraction symbol, it does matter what goes into the calculator first. So in this case, the top number is always going into the calculator first. And you might be thinking, but Miss Woods, if I do that, I'm going to get a number that's less than 1. And a lot of times, that freaks kids out, so then they go and they do the bottom first. They're like, I need the bigger number. Not the case, and don't make that mistake. We always want the top number in first. So in your mind, you should be thinking, my answer is actually probably going to be 0 point something. And already in your mind, maybe that would be giving you an indication of if it's going to sink or float. So if we put it into our calculator, and I'll do it here so you can see in case you don't have a phone or your calculator handy, we have 46.4, and then we're dividing it by our 79.3 centimeters cubed. And what comes out on the calculator is 0.058. Now I'm going to write down initially the 5/8 because as we're learning how to round to the nearest tenth, which is this digit to the right of the decimal, which we talked about last segment, we are using this number to evaluate that. And the saying that I like to use is 5 and above, give it a shove, or 4 and below, let it go. The 8 is above 5, therefore the 8 actually turns this 5 up to a, yeah, you got it, a 6. So when you rewrite your answer, you're going to be doing 0.6 grams per centimeter cubed. And the reason I like to include the units in the actual formula is so you don't forget what you're solving for. Especially with a really hard unit like this with a fraction in it, and you got an exponent, and you're like, what are all those letters and symbols and things? It really makes it easier if you just have this to copy over right here. So you're probably thinking, Miss Woods, 0.6 grams per centimeter cubed, it doesn't mean anything to me. So that's where we're going to take this answer now and have it mean something to you, science related. And we're going to learn what that means or what that looks like here with our bowl of water. So we know that the density of water is 1.0. And we now know that the density of this block, as long as Miss Woods didn't make any errors, or if you were in my classroom or your own science classroom, you didn't either, that the density of this block is 0.6. So really, what we can do is take this number, change it a little bit, and then be able to draw it in this water. And I'm going to teach you how to do that right now. I would like you to come up with some ideas in your head as I'm getting this set up for us about what that would look like. If a number was greater than 1, do you think it would float or sink? If a number is less than 1, do you think it would float or sink? And what about if it was equal to 1? Where would it go then? Okay, so what I'm going to have you do, and I'm going to leave our answer for density up here. Okay, great. Oops, I need to get my... Okay, so we have our density equals. Okay. All we have to do is turn this to a percent. So we're going to turn our 0.6 into 60%. And that amount of the block actually sits below the water. So what I want you to do right now is draw an actual block that looks like visually 60% is beneath the surface of the water, which would leave 40% above the top. So don't draw it like half and half, like this example. I want a little bit less on the top than the bottom. 0.6 density here is actually, it tells us that 60% of this block is below water. Okay, so that's how you would figure that out. So for our last step of our entire essential question, we're going to see if it works. So when I drop this block in here, we should be able to see that about 60% of the side of the block, the height, is indeed underneath the surface of the water. It is a little bit hard to tell through the side, but I really think we accomplished that. You can maybe see with this right now how it's facing you that way. And I think we did a great job. So I'm really proud of you. You could do this same experiment or the same procedure over and over with many other objects. So thanks for working with me today. It was awesome. I'm proud of you for learning, and I'll see you soon.